Okay, so today we are going to do some work notes. I know it's been a long time, but when we left, we were doing kinetic and potential energy, and work was sort of the very last thing that we did, and it was a brief little reading, so I know we haven't had any opportunity to actually talk about it yet. But work is directly related to energy, and that's why it's going to be as part of this unit that we're doing. So just as a quick refresher on energy, remember that energy, we talked about two main types, potential and kinetic energy, when we were talking about the math part of what's happening. And potential energy was the energy stored in an object. And mathematically, as we were doing it, we were talking about energy stored in an object due to the object's position, which, if you remember, is what we call gravitational potential energy. Okay? So that gravitational potential energy told us that potential energy is mass times gravity times height, and that mass and height both could be changed. And since gravity mostly was the same because we stayed on Earth, right, that gravity would be 9.8 meters per second squared. So when we talked about units, we had a kilogram, which is mass's unit. We had a meters per second squared, which was the gravitational unit because it's an acceleration. And then we also had the height that the object was, and that was going to be measured in meters. And remember, height is a distance as well. So the higher you move the object, you're changing the distance of the object from the ground, and that means you're going to have more gravitational potential energy. So this number for potential energy is going to go up as you increase the height of an object. Okay. Also, if you increase the mass of an object, we're also going to have more potential energy as well. Now, gravity, since we're on Earth, doesn't change as long as we say we're on Earth, but there are times where I might give you the gravity of the moon or another planet and ask you to solve for potential energy or solve for the gravity on another planet when we'd cover up G, and we would get potential energy equals mass times height. So we'd do potential energy divided by mass times height. Okay, so that is just a quick refresher on potential energy. We also talked about kinetic energy. Remember that kinetic energy is the energy of motion. Our equation was 1/2 of the object's mass multiplied by its velocity squared. So as a reminder for units again, we had a kilogram for mass, and we had a meters per second for velocity. And since meters per second is squared, or the velocity is squared, we're squaring everything inside the parentheses, which meant the seconds would be squared and the meters would be squared, giving us a kilogram times a meter squared per second squared, or a kilograms meters per second squared. And again, that was also a joule. Okay. So now, just as that refresher, remember a joule is a kilograms meter squared per second squared. Okay, so hopefully that will remind you of what we're doing when we're talking about work now. So work, let's talk about the definition first. So work is the force exerted on an object, over a distance. So you're going to add a force to an object and it's going to move a distance. So it makes sense. You want to pick up a box, it's going to move a distance. Okay? So I'm going to give you kind of a little example. So let's say we do have a box, and you have a person that's going to pick up this box. Remember, I can't draw. So there they are. They're going to pick up the box and they're going to lift it up to, say, a shelf up here. Okay. So work is done only if, so this is really important, if the object moves parallel to the direction of force. So only if the object moves parallel to the direction of force. So what that means is, if I'm going to pick up this object, this box, I'm going to apply a force to it, okay? If the box moves upward and I'm applying an upward force, they're moving parallel to each other. That means work was done, okay? Now, if I set the object back down, the object's direction is going to change. It's going to change downward, but still in parallel with the direction of force. So as long as they're moving parallel, work is done. So an example where work would not be done is if the person picked up the box and did work. So they did work to pick up the box, but then they started walking forward while holding the box. If the person was walking forward, they're holding the box with an upward force, and they're walking this direction, their force would be perpendicular to the direction. In this case, no work was done. Okay? But up here, moving it as long as they were parallel, work is done. You could put yes above it. There we go. So we have to remember that little key when we're talking about was work done. So they have to be parallel, the force and the direction of the object. Okay, so with that said, let's talk about the equation. So the equation for work, our variable for work is going to be W. Okay, a large W. Now we've seen W when we talked about weight, but remember with weight, it was actually force W, so force FW, that is weight. So we're not talking about the same variable. So work is just W by itself, and work is going to equal, since it's the force exerted over a distance, it's going to be just that, a force multiplied by a distance. So whatever the force is on the object and the distance it moves, that's going to tell us our work. So now let's talk about units. Struggling with these pencils. So our units are where we're going to relate it here to energy that we've been talking about. So I'm just going to break down what we already know. We've talked about distance a ton of times. Remember that distance is going to be a meter. We've also talked about force. And remember, force is Newton's second law. Force equals mass times acceleration. And mass is kilograms. Acceleration is meters per second squared. And instead of saying a kilogram meters per second squared, they use a Newton for force. So, force is a Newton, okay? And distance is a meter. And technically that would give us a Newton meter, a Newton times a meter. Well, we don't really use a Newton meter. We actually use what we would do as we break it down again. So since meter is already broken down as far as it can go, let's remind you again, I just talked about it. A Newton is a mass times acceleration. A mass is a kilogram. An acceleration is a meters per second squared. So we have a kilograms meters per second squared times a meter. And we've seen this before in both the energies. Okay, when we multiply kilograms meters per second squared times a meter, and remember up here it would be like a Newton times a meter, we actually get a kilograms meters squared, because there's that other meter, second squared. And since we don't like to say kilograms meters squared per second squared, they use the unit of a joule. So again, a joule is used for work. It's used for potential energy. It's used for kinetic energy. So a joule is a Newton times a meter in this case. Okay, so with that, let's talk about how does it relate to energy as far as the units. And let's talk about this broken down a little bit more. So work, we know, is force times distance. Let's break down distance and force and see what we can get out of that. Distance is at its lowest nothing times anything actually equals distance. So that's already at its lowest. But we already do know that force can be broken down to mass times acceleration. So that's telling us that work actually equals mass times acceleration times distance. Okay, we've seen this before. We've seen this in one of our energies. So mass times what of our two energies has acceleration in it? Well, we don't have specifically the word acceleration, but we use an acceleration for one of our energies, and that is gravity. Now hopefully it's coming back to you. Mass times gravity times height equals potential energy. And since distance and height are the same, acceleration and gravity are the same, and obviously mass is the same, we can say that both work and potential energy would be the same mathematical number. So let's talk about how, again, in our little example up here. Person lifts up the box. I'm not going to draw a person again, but they're going to lift up the box and put this box on a shelf. So we know they did work, right? So now they did a work by moving the box a distance using a force. Now it's sitting on the shelf. What does it suddenly have? It's going to have potential energy on this shelf because it has a mass, gravity is affecting it, and it's just moved a height or a distance. So the number of potential energy would come out mathematically up here with the box would be the same number as whatever the work done to get it there. So whatever the work number is that we solve for the force and distance would be the same number that we would find for potential energy as it sits on this shelf. Okay, so that's how they're the same. So let's do an example of solving. So we'll start with the basic work problem and then kind of mix it around a little bit. Oh, and there is a circle. So I know we all like circles. So circle is going to be work on top, force and distance on the bottom. So again, as a reminder with the circle, with our standard equation, we already know work equals force times distance, but we can prove it by saying, okay, let's cover up W. If we're looking for W, we have F and D on the bottom, and they're next to each other, so F times D equals work, or W. If we're looking for distance, we're going to cover up D and get W on top of F, so work divided by force. And if we're looking for force, we're going to get work divided by distance. Okay, so for this first example, let's do you lift a box with 185 newtons of force from the ground to 0.80 meters up. Okay, so we've moved the box. So we already know we're lifting it in a direction parallel to the force. So we are going to continue with what is the work done. Okay, so we're going to do it just like we do all our problems. We're going to underline what we're given, 185 newtons of force and 0.80 meters. And we're going to be circling what we need, and that is work. And we're going to put out our variables. So we know the equation is work equals force times distance. So we need a W, an F, and a D as our variables. So now we're going to plug in the numbers for the variables. We know that our force is 185 newtons. We know that the distance is 0.80 meters. And since we're looking for force, that's going to be X, and our unit for work, I'm sorry, not force, we're looking for work, and our unit for work is going to be a joule. So we're looking for X joules. Now, since we're looking for W, we're going to use our base equation. W equals F times D. So W is X joules equals my force, which is 185 newtons, and I'm multiplying that by my distance, which is 0.80 meters.